particular material or a couple of materials, maybe the materials which satisfy your requirements for some particular application. You are essentially looking for materials with a specified set of properties. You know what properties those materials should have. And the traditional way of finding such materials have been to do trial and error experiments. You try a material, see how it works. If it doesn't satisfy, you try to modify it, synthesize something new. But such experiments are time consuming, expensive, uncertain. Forget about measuring properties, etc., characterizing. Just synthesizing samples can take you anywhere from 2 days to 2 months, depending on what you are growing. Some of you may be doing experiments, so you would know better than me. But this, I mean, the time scale could vary up to months just for sample preparation. And then this can be expensive because when you are trying to grow a particular phase, you want high purity precursors, which are very expensive generally. Some elements are more expensive than others, but generally any high purity element can be expensive. So therefore, experimental route is time consuming, expensive, uncertain. These are traditional experiments. One could set up high throughput experiments where things are automated, but that does not cut down your costs on the consumables, the elements, the precursors that you would be using. The equipments are all required as in traditional ways of doing experiments. So these are still expensive. In fact, they can be more expensive money wise because you have to have the high throughput automated setup. High throughut DF. So short of experiments, you can do high level quantum calculations, density functional theory. These are again time consuming, not as much as experiments, less expensive than experiments, provided you have the computing facilities set up, which can easily run into crores of rupees. So these are also expensive. Uh, one designed or last 10-15 years, high throughput computations have become the order of doing experiments for a large number of materials, but then that cuts down some human cost, but meaning the time that humans take to intervene between calculations, that time is cut short. You can automate a whole lot of calculations. However, the total computation time does not change, so it is helpful, but up to an extent. So here comes the machine learning part. So suppose you have data, which we have discussed, so I won't need to get into much detail. So suppose I completely eliminate the experimental and the DFT part to start with, and instead of either measuring or calculating properties through DFT, I use my machine learning models. And how we can screen materials using machine learning models for specific applications is something I will discuss today. So this is something that we did a couple of years ago. So here the idea is that, so note the title, leveraging available data for efficient exploration of material space using machine learning. So data availability is a problem in materials. In many other areas, you have tons of data, not in materials. The situation has improved since what it was 2-3 years ago, with some new databases coming up, like Alexandria, which I have talked about. But still, when we did it in particular, there were not so much of data, particularly on magnetic materials. And I'll try to explain to you. So what are we looking for? Here comes the materials part. What are we trying to do? See, most of the electronic devices that you see around, have some magnet in it, whether it's a computer, household appliances, like anything in which you have a motor, industrial large-scale equipments, power generation, you know, plants, or several strategic applications require magnets. And most of the magnets, so we are talking about what are called permanent magnets. I'll explain in the next slide what permanent magnets are. And these magnets most of the time use rare earths. And if you have been reading newspapers recently or listening to news, you know that there is a lot of tension with rare earth elements, in particular in the lanthanide series, neodymium, samarium. So there are supply issues because one country controls the supply chain of these elements, which are absolutely essential components of magnets, which are essential for many technologies. So there is some geopolitical sensitivity about rare earth. And for your information, the most widely used magnet, permanent magnet, is neodymium iron boron. So that is one aspect of problems with magnets. The other aspect is that suppose you want to use the magnet at room temperature, which is, let's say, 300 Kelvin. Now, if you want to use a magnet at 300 Kelvin, its Curie temperature, we are talking of ferromagnets here, its Curie temperature has to be much larger than 300 Kelvin. And typically, the ballpark number suggested by practitioners is that it has to be greater than 600 Kelvin. And on the right, you see a curve which shows the number of magnets versus on the horizontal axis, you have Curie temperature. So as you see, there are many magnets with small Curie temperatures, but if you ask how many are there above with TC above 600 Kelvin, not very many. And Curie temperature is not the only thing that you want. There are some technological requirements, and this is where um, the definition of permanent magnets come in. So the problem is, so what we are trying to do is to discover or design rare earth free strong permanent magnets. Why rare earth free? I have already explained. What do I mean by strong? When you design a magnet, you want it to be strong. The magnetization or the saturation magnetization has to be large. That's what I mean by strong. So the figures of merit, as suggested by technological requirements, is that the saturation magnetization denoted by the quantity ms has to be greater than 1 Tesla. Now, this is typically measured in Tesla. Basically, if you know the magnetic moment, if you take a microscopic view of it, if you know the magnetic moment per unit volume, say mu b per angstrom cubed, if you know that number, you can multiply it with a permeability of space and you get the quantity in units of Tesla. So the technological requirement is that ms has to be greater than 1 Tesla, which approximately translates to 0.085 Bohr magneton per angstrom cubed. Okay, so that is about strong magnets. That is what we mean by strong magnets. Then in permanent magnets, now this requires some explanation if you are not familiar with it. We know that ferromagnets are ferromagnets because all the spins or tiny spin moments inside a ferromagnet point along a particular direction. They all point in one direction. But which direction is this? If the spins are in free space, then all directions are equivalent. Okay, it doesn't matter which direction they point to. But when the spins are inside a lattice, all directions are not equivalent. Right? There are crystallographic directions, and all directions are not equivalent. Let us take some particular direction. Okay, some particular crystallographic direction. You see this red arrow here, and Often it's the crystal symmetry which suggests what a particular direction, spatial direction can be. And I'll explain this by taking the example of a hexagonal closed black structure, HCP structure, in which you have these hexagonal planes, and a natural thing to take for this particular direction is perpendicular to the hexagonal planes. So for the sake of this example, for the sake of illustration, let us assume that this spatial direction is perpendicular to the hexagonal planes. Now, because all directions are not equivalent, when the spins, that is the moments, spin moments, point along specific different directions, the energy of the system does not remain the same. It changes. Now, we start with all the spins aligned along the axis perpendicular to the hexagonal planes. Then we tilt the spins, okay, by some angle theta, and the energy changes. Phenomenologically, the change in energy to the leading order can be expressed as some constant k1 times sine squared theta, where theta is the angle of tilt. Obviously, it has to be sine squared theta. It cannot be sine theta because it doesn't matter which way you change it, the energy has to increase. So now there can be two situations, one in which k1 is greater than 0, the other in which k1 is less than 0. Now what happens if k1 is greater than 0? As you tilt the spins, it costs energy. So the spins would rather like to point along this direction. However, if k1 is less than 0, they would like to tilt more and more till they are parallel to the plane, that is theta equal to pi by 2. So these two situations are called, this is called an easy axis magnet, spins pointing along one particular direction. As you tilt them this way, energy increases till this point, and then it starts decreasing, and when you have completely flipped the spin, all the spins, the energy goes back to the original value. So therefore, for flipping between these two energetically equivalent situations, it has to cross a barrier, which is called the magnetocrystalline anisotropy or magnetic anisotropy energy, MAE. So we want magnets which have large magnetic anisotropy energy, magnets which have large K1. Then the spins cannot flip around very easily because of thermal motion, and they would prefer to point along a particular direction. And that is exactly what you need, for example, in data storage. Otherwise, the magnet would be lost very soon at low temperatures. Okay. So that is, and the K1, the constant, is measured in units of megajoule per meter cubed. And yeah, okay, sorry. Yeah, so the constant K1 is measured in megajoule per meter cubed, and the technological requirement is that it has to be greater than 1 megajoule per meter. I already talked about TC. The ballpark number is 600 Kelvin. It has to be above 600 Kelvin. So these are the requirements. Then there are additional things. It has to be low cost, etc., etc. We are not getting into that. So the problem is to design rare earth free magnets that have large saturation magnetization, large K1 values, TC greater than 600 Kelvin. And of course, if you are designing a new material, it has to be stable. Otherwise, it doesn't make any sense. So for theoretical design, you have to first consider that the material I'm suggesting I'm designing has to be stable. Now, as I said, in many domains of materials, application materials design, there's a paucity of data, and particularly on magnetic properties of materials. Things have improved since then, particularly after the release of the Alexandria database in 2023. This was prior to 2023, and there weren't so much of data. So we took whatever we could get, and the two databases that were released specifically for magnetic properties of materials were Novomag and Novamag. They sound very similar, but these are two distinct databases. These are DFT generated databases for magnetic materials. And look at the numbers. So we took materials all the way up to 50 atoms per unit cell, which is pretty large. 50 atoms in the unit cell is a huge number. But there were only 4,474 materials, whereas Alexandria now has millions of materials, 4.5 million. Now, out of these 4,474 materials, 3,631 were stable. And here by stable, I mean energetic stability in terms of formation energy. So H form, or the heat of formation energy, less than 0. 3,631 materials and 843 were unstable. But we are interested in magnetic materials. So how many were magnetic? 2,963 were ferromagnets, and they reported only ferromagnetic phase, no antiferromagnets here. 668 were non-magnetic. And this, look at these numbers, note these numbers: 2,000, nearly 3,000 materials that are ferromagnets and 668 that are non-magnetic. So this huge imbalance in numbers is what creates problems in model training, something that Dr. Mishra discussed in the last lecture. I'll have something to say about that. Then what we want materials that are easy axis materials, okay, so that the spins don't flip. So how many are easy axis? So first of all, out of these 2,963 materials, whether they are easy axis, easy plane, what kind of anisotropy they have, what is the value of K1, this information is not at all given for all of them. Only for 1131, the information, whether it's easy plane or easy axis, that information is given. Out of which 835 are easy axis materials and 296 are easy plane materials. Now, fine, you know easy axis, these have these have K1 greater than 0. Some are easy plane, which have K1 less than 0. But what is the value of K1? Only for 695 materials, the value of K1 is given. Out of which some 473 has low K1, less than 1. 222 have high K1, greater than 1. But see, out of nearly 3,000 ferromagnets, only for 695 the value of K1 is given. And that is because calculating K1 in DFT is difficult, it's challenging, it's computationally expensive. So that is why there is such paucity of data. It's not easy to always generate quality data. Okay, but whatever we have, and my whole point is that whatever little you have, how can you use those? So what we did was we trained, and this philosophy, we used. I'm showing you one example. I'll refer to another paper where a different group, they have used a very similar strategy for designing materials. The whole idea is screening, okay, and we called it hierarchical screening. So what is the idea? First thing I want is that the material that I design has to be stable. So the first thing, once we have the candidate materials, first thing we do is classify them, stable or unstable. That is whether H form is less than 0, greater than 0. We don't do the regression right away. First, the classification. Is H form likely to be less than 0 or greater than 0? If it is less than 0, it is stable. We collect such materials and then do a regression. What is the value of H form? Fine. If it turns out to be, the prediction turns out to be less than 0, we are even more sanguine that it is a stable material energetically. Next comes, so just follow the arrow, okay, clockwise. Next comes a classification model. Is it is the stable material magnetic or non-magnetic? Binary classification, we have talked about it. And then we collect all the magnetic materials, materials that are classified as magnetic. Then we apply a regression model only on those materials and predict what the magnetization is. Fine, we get a value of magnetization. Is it greater than 1? Is it predicted to be greater than 1? If it is predicted to be greater than 1, it's of interest to me. The rest are thrown out. Then the materials that pass through this test, a classification model is applied to them. These magnetic materials with large magnetization, do they have easy axis anisotropy or do they have easy plane anisotropy? Now we collect the materials that are predicted to have easy axis anisotropy. And then comes the last classification model, is the fine K1 easy, the materials are easy axis anisotropy. That means K1 is greater than 0. But is it greater than 1 or less than 1? So is it low anisotropy or high anisotropy? And finally, our interest is only in the high anisotropy materials. So there are 6 models here, as you see, 4 classification models, 2 regression models, and what they are doing is basically, you see this figure on the right bottom. I start with a large number of materials, check whether they are stable. That's the first level of screening. What is the H form value? Second screening. Then magnetic or non-magnetic, only the magnetic materials pass through. After that, what is the MS value? Only those with MS greater than 1 pass through. Then is it easy axis magnetism anisotropy or easy plane anisotropy? Only the easy axis materials pass through. And finally, is K1 greater than 1 or less than 1? And only the K1 greater than 1 materials are collected. Okay, so that's this. Sorry, this picture captures all the idea. You have a sequence of filters, and each time you select only a certain set of materials depending on what properties you want them to have. So that is the idea of hierarchical screening, and we have 6 models here. So what are the features used? These are things that we have discussed. I have taught you some set of features that capture stoichiometry or composition weighted chemical properties, like composition weighted atomic number, electronegativity, period number, group number, valence electrons, etc. The top 2, the red ones, are the stoichiometry norm and stoichiometry entropy. And finally, the sign matrix eigenvalue, which brings in some information about the structure. So, a total of 68 features. All right. Models that were trained are neural network. We have explained that, and the random forest model. You don't have to look at all these numbers. All that I ask you to do here is just focus on the top 2 tables. First is the stability classifier, stable or unstable, binary classification, and we train 2 models, as I said. This the neural network and the random forest. And as you see, not much difference between the 2, but if you look at any of the metrics, the random forest does slightly better than the neural network. On the right top, you have formation energy predictor, the regression model. Again, the random forest does slightly better than the neural network. So R2 score, for example, is 0.86 for the random forest, 0.82 for neural network. Mean absolute error is also lower for the random forest model. Same is the Pearson correlation coefficient between the target and the predicted values. So this is a general feature of comparison between the performance of neural network and random forest when your data size is not large. Quite often, random forest outperforms neural network. Although when you have large amount of data and you have the right set of features, neural networks is generally better than random forest. But you should be aware to the fact that for small data, often random forest models work better. Okay, all right. So the rest are the same, but that's not what so that is one important point, of course, I wanted to convey. The other thing I want to show here is, and we may spend a bit of time here, is the the effect of imbalance in data. So look at panel A, it's the stable, unstable classifier. And then what you are shown here are the confusion matrix. So there is this random forest model. RF is the random forest. And you see on here is the actual level, stable materials, unstable materials. And these are the predicted levels, unstable, stable. So these off-diagonal blocks are misclassifications. And we showed that, I showed you, let us go back to that slide once more here. So you see, there are 3,631 stable materials and 843 unstable materials. So there's far fewer unstable materials compared to stable materials. As a result, the model misclassifies unstable materials. So what is the total number of unstable materials? So 108 of them are classified correctly. 61 of them is unstable, classified wrongly as stable materials, right? So now you ask, what is the fraction of unstable materials that are misclassified? That would be a number which is 61. Let me see if I can bring up a calculator. Yeah. So 61 is, these are misclassified, and the total number is 61 plus 108, which is 36%. So 36% of the unstable, that is the minority class samples, are misclassified. That is because this is the test set performance, because overall the number of unstable materials is small. So therefore, when I do test train split, I have again fewer unstable materials. In the training set also fewer unstable materials. So the decision boundary is not learned properly. Okay, so that is why we train the next model, which is RF up. So what is RF up? An upsampling is done there in the minority class. You have the majority class samples, which are the stable materials. Then the minority class, that is the unstable materials, are sampled more than once randomly till you have the same number of unstable materials in your training set as the number of stable materials. So let us see what is the misclassification rate in this case. Of course, the total number remains 169, but in this case, the number of materials that are misclassified reduces to 49 instead of 61, and that rate is 29%. So it improves from 36% to 29%, the misclassification. You can similarly calculate on the right is panel B is the magnetic non-magnetic classifier. Again, we have many more ferromagnetic materials than non-magnetic materials. So model training is somewhat biased towards the majority class, the magnetic class. So the non-magnetic materials are misclassified, and the misclassification rate by random forest is 39%. And when an upsampling is done, it reduces to 29%. I hope I have put the right number, but you can easily calculate it. So this upsampling reduces this misclassification rates of the minority class. A similar thing can be observed when easy, so panel C is easy axis versus easy plane classification, and it is even worse, as you see. The easy plane is this is fewer in number, and the misclassification rate is 76%. And when an upsampling is done, that becomes somewhat better at 52%. And the high K1 materials, high K1 or low K1, that is the panel D rather than, these are all, let me correct this. So this I'm talking about panel D. Here I'm talking about panel D. Okay. So if you look at the confusion matrix in panel D, I have not even shown the random forest model. The random forest model misclassifies high K1 materials by 46%. It misclassifies 46% of the high K1 materials. When an upsampling is done, that reduces to 40%. But it can be further improved by using what is called this ROC curve. You calculate true positive rate and true negative rate, and you take their geometric mean and optimize that by changing the decision boundary. So this was discussed in the last lecture, and when you take the optimal value of the decision boundary, you get a misclassification that reduces to 28%. So these were the things that were done. So these are just examples of how imbalanced data sets can complicate your model training and in the materials domain, and what you can do to overcome those. All right. So these are about classification models. These are the regression models. Remember, we had two regression models. One is formation energy prediction, the other is magnetization prediction. In both the figures, the horizontal axis is the DFT calculated value, and the vertical axis is the predicted value. Ideal prediction, if all predictions are correct, would lie on the straight line with a slope of 1. Some deviations, only natural, because this is a statistical process. Formation energy prediction is better, particularly those with large, small formation energy, small negative. Magnetization is a tricky business. Generally, it has turned out that training models to predict magnetization is harder than training models to predict formation energy. In fact, quite often only composition weighted chemical information gives reasonably good results for formation energies, but it would hardly work for magnetization. And it is also found, and I show you this work, there are other works in the literature which find that when the magnetization value is large, the predictions are better. The models perform worse when magnetization values are small. So these are some general observations. But otherwise, this is the performance, and the R2 scores in both cases turn out to be roughly similar. Okay, so once again, these are the performance of the two models. No, I'm sorry, not two models, but 6 models. 2 regression models, and 4 classification models. And as you see these figures, the table should just highlights the performance of the regression models. Once again, we have seen these numbers, but the bottom figures show the performance of the classification models. And as you see that as the number of data set sizes, so on the left bottom you have, so this part you have the performance of the models in terms of F1 scores, and on the right you have data set sizes. So as the data set size decreases, the model performance becomes worse. So therefore, volume of data, amount of data for your model training is very, very crucial, needless to say. However, what this discussion also carries, the message it carries, is that with some innovation, in case you are stuck with small data, with some innovation, you could still maybe make use of it. Okay. All right. So again, these are numbers we have seen. Now the question is, so far I have been talking about training models and how they perform and so on. All that is fine, but what do we do with these models? Okay. So I told you we had some 3,000 materials. Let us look at those numbers once again. So we had a total of 4,474 materials. And yeah, so look at this figure. It may seem puzzling, but let me slowly take you through this figure. So look at this figure in the sense of a Venn diagram. Okay, so these are different circles at different sets. So the complete material set or complete set of stable materials is the biggest circle, C. Okay, that's the complete set. Now out of these, this subset F, okay, so this circle, everything inside it, that's the set F, is the set of ferromagnets, stable ferromagnets with large magnetization. But that's only a subset of the total set of materials. Now inside F, there is a smaller subset of materials that have uniaxial anisotropy, right? The rest would be easy plane anisotropy. By uniaxial, I mean easy axis anisotropy. And out of those, there will be some materials for which anisotropy information is given. So out of this complete set of materials C, stable materials C, only for this tiny fraction, we have all the information about magnetic anisotropy. So therefore, the question is, so these materials we know what is the magnetization, we know what is K1, we know whether these are easy plane, easy axis, whatever. Now the question is, can we use our models to identify materials from the set F that are not included in this subset? So the rest of F, so F minus A, if I look at the set F minus A, there could be materials that satisfy our requirements. So now what we do is we apply the models that we have trained on materials in the set F minus A. And this is how it goes. So look at the left figure. So this is the hierarchical screening one is talking about. So we find that there are 762 materials. So F minus A, we look at those materials, take those materials. These have heat of formation or formation energy less than 0, high magnetization greater than 1 Tesla. But whose anisotropy information is unknown, and there are 762 materials in that set. Now, out of these, we select the ones, and this is a material aspect. This is where you need domain knowledge. We select the ones in orthorhombic, tetragonal, and hexagonal crystal structures. Why? If you look at any data set, you will find that it is materials in these three structures, largely in these three structures, that are large magnetic anisotropy. Why? That requires one to get deep into physics discussion, crystal symmetry, point group symmetry, spin orbit coupling, crystal field splitting, etc., etc. So, which is of course beyond what we can do here, but the bottom line is that these crystal structures tend to have large magnetic anisotropy energy. All right. Now on these 312 materials in this block, we apply our models. The first model we apply here is it an easy axis or an easy plane anisotropy material? Easy axis or easy plane? And 100, and our interest is in easy axis materials, and 155 are classified as easy axis materials, okay, by our model. Now we take this 155 and apply the next model. Do these have large K1 greater than 1 or small K1 less than 1? And 14 of 155 are predicted to have large K1 greater than 1. And finally, but then these are just model predictions, though they could go wrong. So how do we confirm? Well, we confirm because the models have been trained on DFT data. We confirm these with DFT data. So we do DFT calculations, calculate all these properties, magnetization and anisotropy, etc., on these 14 materials. And 12 out of 14 turns out to have large magnetization. Sorry, large magnetization was already taken care of. So 12 of these materials are predicted to have large uniaxial anisotropy, large easy axis anisotropy, okay, greater than 1 megajoule per meter cube. So not bad. By doing DFT on 14, 12 materials turn out to have all the properties that we want. But what did we gain in the process? See, if I had to do 312 DFT on these 312 materials, this is the time. This bar is sort of a measure of the time, computational time we would have required. Instead, when we do DFT on 14 materials only, so there's a 95% saving of computation time by applying these machine learning models for screening. Now here what we did was we explored that part of the database that we already started out with, which did not have the complete information to arrive at these 12 materials. But can we go beyond that data set? So in fact, one can do that also. Nothing fancy, you just do substitution. You substitute some atoms in the existing materials by some other atoms. There is a logic to it, which is beyond what we can discuss in a 1-hour lecture. But, that's basically what we did. The paper discusses all the details. And we designed 374 new materials. And now we apply all 6 models, right? Because these are completely new materials. So we checked for their stability. 202 of these were predicted to be stable. Then we passed these stable materials through magnetic, non-magnetic classifier. 201 were predicted to be magnetic. Then we applied the magnetization regression model. 82 of the materials were predicted to have magnetization greater than 1 Tesla. Then the easy axis, easy plane classification model. 67 turned out to be easy axis. Then the large K1 or small K1 classification model, and 29 were predicted to have large K1 values greater than 1 megajoule per meter cube. So we do DFT on 29 materials only. So 374 versus 29, 92% saving of computational time. And once you have trained the models, these property prediction models practically don't take any time to make these predictions. And out of the after DFT, 11 of these 29 materials are predicted to satisfy all the required properties. So finally, we end up with 12 here, 11 there, some these materials by doing minimal amount of computation. So this is how. So the point is, I try to explain to you what is the idea of hierarchical filtering, what is material screening using pre-trained models, surrogate models. These are some of the terms you will hear. This is what it means. It's a very simple idea. You have a sequence of models, you train them on existing data, and when you have a new set of materials, you apply them as required and you screen them one property at a time, and finally you come up with a very small number of materials which you first confirm with DFT, and the ultimate test of course has to be in experiments. Can someone synthesize this? That's a bigger question. It's not as simple as doing a DFT calculation, so I'll leave that aside for now. And just to show you, these are some of the interesting materials we found. So these are the materials that already existed in the data set, but their anisotropy properties were not calculated. And this is one, Fe12Ta4, this one, and this one is Fe12Ta2. So these are alloys, iron and tantalum, and this is its distance from the hull, and this much is its distance from the hull. They are not very far from the hull. Maybe it may be possible to synthesize this. Okay, and these are obtained by modifying some of the existing materials. All right, so that is the idea. The specific materials is not of importance to you at this point, but the idea of hierarchical filtering, how you apply surrogate models to screen materials and arrive at a set that satisfy desired properties is what I wanted to convey to you. Okay, all that is fine. So we come up with a few materials that have large, that are stable, that have large magnetization, large anisotropy, and we also calculate their distance from the hull, which is easy to do. I have shown you how to do it. You can get materials from the materials project or OQMD, or just put in the value of your material on the OQMD, that web-based interface, and you will get its distance from the hull. There are codes, for example, which do these kind of plots and tell you what the distance from the hull is. This is for the binary material, binary iron tantalum material. This is the ternary phase space hull for materials. Here, Fe13Mn3N2 and Fe12Mn4N. Okay, the last slide that I have today is what about TC? Started out by saying that TC has to be greater than 600. So far, I have not talked about TC. And that is a problem. TC is a problem. TC is a problem for the following reason, that there are no big databases for TCs that are already created, reported in a neat way. We trained the previous models based on DFT data. It is very easy to calculate structure, energy, even magnetization with DFT. We already saw, or at least I told you, calculating K1 in DFT is not easy. Calculating TC in DFT is impossible. DFT doesn't directly give you TC. Okay, impossible in the sense that you have to do a lot more work after DFT to get an estimate of TC. Exact calculation, impossible. So, and DFT being a zero temperature theory doesn't give you TC. So there are no theoretical databases for TST. There are experimental databases. Well, not really databases. There was some collection. But sometimes there's a problem in experimental databases. It's the same material, at least the same composition, can we reported to have two different TCs, slightly different TCs, in two different experiments. Maybe because the materials were prepared, the processes were slightly different. What the, the final sample was, what it contained may vary slightly. I'm sure those of you who do experiments know this very well. So therefore, the TC can vary somewhat, and it's not like a neat number that typically we get in calculations. So, but there are ways one can take care of that by adopting something that will take the mean value, or if there are more than several times the material appears, I'll take the value that appears most of the time, etc., etc. There are, you have to innovate depending on what you have. The bigger problem is, and that is this line, the structure is not always reported. So remember some of the features that we talked about. Creating those features require knowledge of structure, the lattice vectors, where the atoms are sitting, etc. And these experiments often don't give that. They may give you that this is a hexagonal structure or that is a cubic structure, that much. Where are the atoms? What is the lattice constant? They may give, may not give. They'll give you the composition. So what you definitely have is composition and TC. What you most often do not have is what exactly is the crystal structure. So there are two papers I will cite here. The first one is from Stefano Sanvito's group in Ireland. The second one is from Tanushree Sahadas Gupta's group in Essenbo Center. Tanushree et al. Tanushree's work, Anita Haldar, her student, what they did was essentially what I talked about so far, a screening of materials. They were not looking for rare earth free magnets, they were looking for a class of rare earth lean magnets, that is materials containing very little, tiny amount of rare earth. Similar in spirit, but different in detail. But the method was very same. You have a set of initial materials. Are they stable? What is their magnetization? What is their anisotropy? So hierarchically, you filter and arrive at a small set of materials. Whereas Nelson and Sanvito did a completely different job. Their work is about so that is that PhysRep materials paper. Their work is about predicting TC, Curie temperature of ferromagnets. What they did was they took data from these sources: the Atom Work database, Springer Materials database, Handbook of Magnetic Materials. And as I said, they got composition and TC, but not structures. And here I should make a comment that data exists. When someone does a measurement on suppose studying a new magnetic material, doesn't report the complete atomic crystal structure, but reports that this is the composition, this is the material we are studying, and this is the TC. And these are all buried somewhere in the paper, either in the text or in a table. And there may be thousands of such papers. And it is humanly impossible to search out all these papers over decades, maybe close to a century, and then create a database, right? That's just impossible, at least within a reasonable time frame. So what one can do and has been done is to apply language models, natural language processing models that can parse the existing literature, read out the papers that exist, and then extract this information. And this way, quote unquote, they have created a database of Curie temperature of ferromagnets as well as Néel temperature of antiferromagnets. And so this is just an information. So that is in the second reference, you will find that. But I'm talking of the first point here. This data from Atom Works, Springer Materials, and Handbook of Magnetic Materials. These were used to train the models for TC prediction by San Vito. So it's a regression model, predicts TC. What are the features that they used? For obviously, they cannot use features like ACSA for sign matrix because structure is unknown. So they basically used these features essentially. You can look at their paper for more details, but composition weighted chemical information is essentially what they used. Um, so the point is, we may tend to think that, well, because the structure is not known, we can't really do anything, we cannot train a model. But then what they did was just went ahead and trained a model without structure information and see what they got. And what they got is not completely trivial. No, it's not completely useless. They got a model with an R2 score of 0.87 and a mean absolute error for TC, that is 57 Kelvin. And same thing here, for larger TCs, the prediction is better. And when the TC is small, the prediction is somewhat worse. And one would generally be interested in materials with large TC. So that way, we are better off. So yes, you know, uh, we computationally design materials. We cannot computationally calculate their TC, but if we have such a model, then we can predict the TC and at least decide whether the material is likely to have a high TC or a low TC. So that is all I wanted to discuss today. Uh, some of you requested. So tomorrow, so next class, that is Friday, we can have an interactive class. Depending on how much time that takes, we can discuss some more use case scenarios also. But primarily, it will be a tutorial kind of class where you are free to ask your questions, discuss your projects, and if then time remains, I may discuss one such example. Okay, if there are more questions or any questions, you can ask or type in. Otherwise, well, I'll give you a minute and after that I'll close. Other descriptors. So Shulagna is asking question. Can you discuss about other descriptors in the next class? I have already discussed other descriptors in one of the earlier classes. If you go back to my slides, I discussed MBTR, sign matrix, Ewald matrix for calculation of formation energy. With examples, how they perform on a given data set. I have already done that. If I can think of another, yeah, sign matrix, you should get some reasonable, whatever, some result. It was not very good, but remember, it also depends on your data set size. So, what was the size of your training data? I mean, yeah, results will not be very good if your uh, how many training samples did you have? Yeah, that's too small, perhaps. If you go to that paper, you go to my oldest slides, I'll show you which ones. Just give me a minute. If I have them here, I'll show you. Yeah, this is what I had shown you. The mean absolute error, the best thing they got was with MBTR 123, somewhere, let's say around zero point 0.1 EV per atom. But look at their sample size of the order of 200,000. You have only 2,000. So that's an issue. And with sign matrix only, let us look at their number also. With sign matrix only, it's slightly above 0.15 electron volt per atom. So what was your number, if you remember? Or you can tell us next time in the next class, okay? All right then. So next class, the first part will discuss your questions, your projects, if you have any questions about those. And after that, we may discuss some other examples. All right, so that's all for today.